The title of my presentation is 25 Years of Sensor Array and Multi-Channel Signal Processing. My name is Willett, and here's my email address and my personal website. Now the outline of this talk. So first is a quick introduction. Then we talk about 5 main technological advances in the SAM area. So including beamforming, DO estimation, so direction rival estimation, sensor location optimization, packet source localization, and MIMO arrays. And then we also introduced 6 new developments in the SAM area. So including graph signal processing, or GSP, for sensor networks, and tensor-based array signal processing, Quaternion valued array signal processing, 1-bit and non-coherent or magnitude-only array signal processing, and machine learning and AI for sensor arrays, and array signal processing for next-generation communication systems. And then finally is a brief conclusion. So this presentation is based on our publication in the 75th anniversary of Signal Processing Society special issue of the IEEE Signal Processing magazine, and with the same title. So first is introduction. So sensor array multi-channel signal processing, or SAM. It has a long history with typical research topics, including beamforming and DO estimation at its early stage. And the past 25 years have seen an explosive growth of research activities in this area, and significant progresses have been made in a wide range of theoretical and application areas of SAM. And although traditionally their applications have been mainly limited to the defense sector, such as radar and sonar, nowadays we can see their impact in our everyday life, including beamforming for ultrasound imaging, and synthetic aperture radar for remote sensing, auto radar for autonomous driving, and microphone arrays for human-machine interface, like Amazon Echo, and multi-input, multiple-output antenna arrays for Wi-Fi and mobile communications. Since it's impossible to give an exhaustive list of all the advances made in the SAM area, so here I will just focus on 5 major topics. One is beamforming, so including robust adaptive beamforming and the frequency invariant beamforming, and DO estimation, including sparsity-based and underdetermined DO estimation, and sensor location optimization, and target source localization based on sensor arrays, and MIMO arrays, including MIMO radar and MIMO for wireless communications. Then 6 new developments will be presented to give an indication about possible future research directions. So including graph signal processing for sensor networks, and tensor-based array signal processing, Quaternion valued array signal processing, 1-bit and non-coherent sensor array signal processing, machine learning and artificial intelligence for sensor arrays, and array signal processing for next-generation communication systems. First, these 5 main technological advances in SAM. So the first topic is beamforming. So beamforming is a classic SAM problem. So it can be classified into narrowband or wideband beamforming according to the relative bandwidth of the signals, or adaptive and fixed beamforming according to its relationship with the received data. So adaptive, it means it's data-dependent beamforming, and fixed beamforming is also called data-independent beamforming. And it can be classified into analog and digital beamforming according to its circuits implementation. In the past 25 years, so 3 main developments are highlighted in this talk, so including robust adaptive beamforming and frequency invariant beamforming, FIB, and hybrid beamforming. Hybrid beamforming is a combination of digital and analog beamforming techniques. So in this part, we just discuss the first 2 and leave the hybrid beamforming, leave this part to the section about MIMO arrays. So now for robust adaptive beamforming, so consider this M sensor array with K narrowband impinging signals. Then here is a standard array model. So XT is the received signal vector, A is the steering matrix consisting of big K steering vectors, and ST is a source signal vector, and NT is a noise vector. Given this array model, so the beamformer output YT is just the instantaneous linear combination of the received spatial samples XMT. So here is a formulation, and you can put all the coefficients Wm into a vector, is a weight vector of the beamformer. So it's given by this WHXT. And then for beamforming, if you want to receive the desired signal from angle θ0 and surprise all other signals or interferences, then you can use this Kaplan beamformer. So this is the formulation. This part is a constraint WHA θ0 equal to 1. That means, okay, the response of the beamformer to the desired signal should be 1. And this part, the cost function, is the power of the beamformer output. Or normally, because we assume it's zero mean, so it's a variance. So you can say this is a minimum variance distortionless response beamformer. So basically, it's called MVDR. So minimum variance distortionless response beamformer. And you can add more constraint, linear constraints here in the constraint part. So you can have a general linearly constrained minimum variance beamformer, or we call it LCMV beamformer. So this Kaplan beamformer is just a special case. And in practice, certainly this R is not available. So we can use this finite number of data samples to estimate this R, so given by R hat. So the Kaplan beamformer is very sensitive to model mismatch errors. That means, okay, if you assume you know the steering vector of the desired signal, if there's any error in this assumed steering vector, then the desired signal will be treated as interference, will be suppressed in the beamformer output. So it's very sensitive to the model mismatch errors. And to solve the problem, so basically make the beamformer more robust. So one well-known technique is diagonal loading. So this is a diagonal loading solution. Basically, is trying to limit the norm of the resultant beamformer weight vector. If you limit the norm of this weight vector to some small value, then basically you are trying to constrain the gradient of the beamformer response around the assumed steering vector of the desired signal. Around that area, you try to limit the gradient to a small value so that the desired signal will not be suppressed too much in the beamformer output. So that's diagonal loading. And one prominent development in this area is the so-called worst-case-based robust adaptive beamformer, where the beamformer response is forced to exceed unity within an uncertainty site of steering vectors. So here, this is formulation, this equation 4. So again, you're minimizing the output power or variance of the beamformer subject to these constraints. In these constraints, so A θ0 is an assumed steering vector, and A tilde is the possible true steering vector of the desired signal. And there's error between these two. So given by this error vector E, and this error vector is norm-bounded by this epsilon here. So this constraint makes sure the beamformer will have a response larger than or equal to 1 for all possible directions of the desired signal. To solve this problem is converted into the following form using the worst case optimization. That's in this part, in this formulation 5, the constraint is, okay, set the imaginary part of this response to be 0. And then you can remove this constraint, this part, and then you can just take the real part of this response to satisfy this requirement. Because imaginary part of this response does not really matter, because we can always rotate the response and to make sure the imagined part to be 0. So you have this simplified formulation. And both the Kaplan beamformer and the worst case robust beamformer require estimation of the covariance matrix. And it's a challenging task when only a small number of snapshots is available. And one solution to the problem is the family of iterative adaptive approach-based methods, which can still work for the extreme case with only one snapshot. There are also methods for estimating the covariance matrix with only one snapshot. Okay. Another notable contribution for robust adaptive beamforming is based on interference covariance matrix reconstruction and steering vector estimation and its various extensions. You can find details from reference 10 about this method. And now for frequency invariant beamforming. So it's a wideband array, basically. So for wideband array, the model is different. You see here, you have this received signal vector xt, and here st is the source signal vector. But here you don't have the steering matrix anymore. It's still matrix, but it is a tilde. And this matrix is the mkth element of this matrix is given by delta t minus t tau mk. And this tau mk is a delay. It's delay of the kth impinging signal at the mth sensor compared to some reference point. So here, this star is a convolution. So this matrix and convolved with this st. So it's not a multiplication, direct multiplication. It's a convolution. As a result, so wideband beamforming is achieved through a series of type delay lines or FRIR filters in its discrete form. So this is a standard wideband beamforming structure. So you have received signal, you delay them by different amounts, and then you have this weight vector, then its output. So in the wideband array, so the beamformer output is not an instantaneous linear combination of the received signal anymore. There will be different number of delays involved. In general, so beam width will increase with the decrease of frequency since the relative aperture of the array becomes smaller. So with the increase of the wavelength. Therefore, so one unique problem for wideband beamforming is how to achieve a frequency invariant beam response or beam pattern. So based on simple Fourier transform relationship, a systematic and consistent approach was developed to design fixed frequency invariant beamformers for 1D, so one-dimensional, two-dimensional, and three-dimensional arrays, and for both continuous and discrete operators in these references. Okay, and furthermore, a series of least squares-based FIB design methods were proposed with closed form solutions and applicable to arbitrary array geometries in reference 5 and 14. In the very basic form of this method, so given the desired response, big PD, omega theta, big omega is a normalized frequency. Given the desired response and the design response over the frequency range of interest and the angle of interest, then the design is to minimize, okay, this cost function. So in this cost function, you have two parts. And the first part, you see omega r is a reference frequency. You can select this frequency yourself. And so P omega r theta is the design response for given weight vector. And PD omega r theta is the desired response for this frequency omega r. So you measure the difference between these two. So you minimize this part. It's a standard least squares formulation for one single frequency. And this part, you see, there's no desired response involved. You only have the design response. So P and P. So P omega theta and P omega r theta. Basically, you see, you are measuring the response variation of the resultant beamformer across frequencies. So if it's frequency invariant, then this second part will be 0. And if it's a frequency environment, again, so this part, you measure the error between the designed and desired responses. You only need to measure this error for one single frequency. So you don't, for the first part, you don't need to calculate the error for all frequencies. You only calculate this error for one frequency only. So you combine these two parts together and minimize it, you can find a closed form solution for this problem. And here's a design example. The frequency range is 0.3 pi to pi, and it's a uniform linear array with 10 sensors and a type delay line length of 20. So you can see the response is frequency invariant. So FIB, so it can be used certainly for beamforming, but it can also be employed to transform the wideband array signal processing problem into a narrowband one, so that existing narrowband solutions can be applied directly to the FIB output. So you can do narrowband DO estimation and narrowband beamforming to achieve a wideband effect through this FIB network. And the second part of the cost function in 8, so basically this part, you can incorporate this part into the adaptive beamforming process to realize adaptive FIB instead of relying on the FIB network. So you can basically achieve adaptive frequency invariant beamforming. Okay. The TDL-based wideband beamforming structure could be replaced by the sensor delay line-based structure, where multiple sensors are placed behind the original array sensors in place of the delay lines for effective wideband beamforming. And such an SDL-based structure may prove to be very important for the coming terahertz or sub-terahertz communication systems, where the delays required for effective wideband beamforming or beam steering may be too short to be implemented in practice. So basically, for very high frequencies, if you want to steer the beam to different directions, the delays required will be very short and very difficult to implement. So you can, instead of doing that delay, implement that delay directly, you can use sensor delay line to achieve that. So this structure may prove to be very useful in future terahertz or sub-terahertz communication systems. Now, the second topic is DO estimation. So DO estimation is another core SAM research area, and in its simplest form, you can just use beamforming to achieve DO estimation. And more advanced super resolution solutions have also been developed, such as music or S-Bait and so on. And in the past 25 years, so inspired by developments of compressive sensing, there are two important advances. The first one is a sparsity-based DO estimation framework, which, unlike the subspace-based one, can deal with coherent sources. And then another one is called underdetermined DO estimation, based on various signal properties such as non-circularity, non-Gaussianality, and also based on the co-array concept, like sum and difference co-arrays. And here the underdetermined means the number of signals is larger than or equal to the number of physical sensors. So to introduce the basic idea for sparsity-based DO estimation, now we consider the discrete version of the model. So it's I, the index is I, not T animal. So it's xi equal to A times Si plus Ni. And for this ith snapshot, basically for single snapshot, to exploit the spatial sparsity property of the source signals, so we can create a search grid of kg, big kg potential incident angles. And then for each angle, you can have the corresponding steering vector. And then you put them together, you can form this overall complete steering matrix. And similarly, you can form this kg by one column vector, signal overall complete source vector, basically. And then you have this new representation. Okay, it's A times S, it's G times SG. So they are overall complete representation of the steering matrix and the source vector. So to find the directions of the source signals, so you can have this formulation. So basically you have this constraint. It's a reconstruction error. So this xi is the received signal vector. You try to reconstruct this received signal using this SG and A theta G. You find this SG, sparse SG, and you minimize the number of non-zero valued entries in this SG. So you use L0 norm to represent that number of non-zero valued entries. And then you minimize this, and the locations of the non-zero entries in the resultant SGI represent the corresponding DOE estimation results. Now, L0 norm is non-convex, so we can use L1 norm as an approximation. So you minimize the L1 norm, so you get the final formulation for this method. And when multiple snapshots are available, you can perform DOE estimation using this formulation 13 snapshot by snapshot. Certainly is not effective. So you can use what? You can use group sparsity to have a joint estimation of DOEs. For group sparsity, so suppose you have a big P snapshots, and then you put them in a matrix. So basically you have this equation, this new model 14. So big X, big A, big S, big N. So they are matrices now. And then to introduce spatial sparsity, similar to the single snapshot case, and we can construct this over complete source matrix. So over complete steering matrix. So you have this model 15. Then you think, okay, if there's no signal for one direction, then the corresponding row of this matrix SG will be 0. And so if there's a signal, then that row will not be 0 valued. The idea is, okay, you calculate the L2 norm of each row vector in this SG, this matrix SG, and put this L2 norm into a vector. And then you calculate the L1 norm, you minimize the L1 norm, and subject to this, again, it's a reconstruction error. So limit the reconstruction error to a small value epsilon, and then you minimize or maximize the sparsity of this SG height. And we also call this the SG, the L1 norm of this SG height is also called the L21 norm of the matrix SG. Okay, and then locations of the non-zero entries of the resultant SG height after optimization are then the corresponding estimation results. And certainly a problem with this is, with this formulation, this solution is, if you have a large number of snapshots, big P, so you have a big P, then the complexity will be very high. And to solve the problem, we can perform singular value decomposition to X. So you can reduce the dimension, and you have this L1 SVD method. Or you can use the covariance matrix to form a virtual array directly. Okay. Now for underdetermined DOE estimation. Underdetermined DOE estimation can be achieved by exploiting non-Gaussianality, non-circularity, or non-stationarity of the signals. However, the most important development is through constructing various sparse array structures for virtual co-array generation, such as coprimary arrays, nested arrays, and their numerous extensions. And the difference between this part and this part. So first part, okay, for underdetermined DOE estimation, you can exploit the statistical properties of the signal, non-Gaussianity, non-circularity, and non-stationarity, right? But the second part, based on co-array generation, you only need to assume the source signals are uncorrelated with each other. Certainly is for the second order co-array case. Okay, so for second order statistics-based co-array generation, to assume the signals are uncorrelated with each other, you don't make any other assumption for the statistics of the signals. Then for this method, you can just vectorize the covariance matrix. Here is the covariance matrix standard result, and you vectorize this, you obtain equation 19. And Z is vectorized result, and that is the virtual signal. And you have this S tilde is virtual source signal, and this is given by the this vector given by sigma 1 squared, sigma 2 squared, and so on. Basically, they are the power of the source signals. And this big A tilde theta is a virtual steering matrix. And its virtual steering vector, small a tilde theta k, is given by the Kronecker product of this original steering vector and its conjugate. So although there are repeated entries in this RXS, in this covariance matrix, the number of virtual sensors corresponding to the difference covariance is much more than that of physical sensors, and the equivalent source signals share the same spatial sparsity with the original impinging signals. And this model 19 is similar to the single snapshot array model. So sparsity-based DO estimation methods for single snapshot can be applied directly to find the directions of the source signals. And instead of employing a sparse array, it's possible to extend the co-array concept to different frequencies, where a single URA can be used. So you don't need a sparse array, you just use a standard URA with two continuous wave signals of co-prime or other different frequencies. And also you can extend it to the wideband case through frequency decomposition and employing multiple frequency pairs. The group sparsity concept can be applied to general underdetermined and overdetermined wideband DOA estimation. Like in traditional case, focusing can also be employed for sparsity-based wideband DOA estimation to simplify the problem to a single reference frequency. And one interesting observation for the wideband case is the sensor spacing can be larger than half the wavelength corresponding to the highest frequency of the signal without causing spatial aliasing problem. On the contrary, an improved estimation performance can be achieved for larger spacing due to increased aperture. Here's some experimental result. So you see it's a microphone array, it's a co-prime array with 8 microphones, and we have 10 signals. The bandwidth is from 5 kilohertz to 10 kilohertz, and sampling frequency is 20 kilohertz, and this is the result. You can see all the signals, their directions have been distinguished. Now, the third topic is sensor location optimization. So in many applications, the array's geometrical layout is assumed to be fixed or given in advance. However, it could be optimized, provide additional spatial degrees of freedom to improve the performance in terms of either beamforming or DOA estimation or both. For beamforming, given the non-convex nature of the optimization problem, traditionally is solved by genetic algorithms similar to the annealing and so on. With the development of CS, a new CS-based framework with a theoretically optimum solution has been developed for sensor location optimization for fixed beamforming, and followed by further work in adaptive beamforming and with robustness against various array model errors considered to okay. And for DO estimation, the main efforts have been focused on the co-array design to increase DOF, the degree of freedom for underdetermined DO estimation. And in this part, we focus on the problem for beamforming. To illustrate the idea, so we consider a narrowband linear array structure with M sensors, where the distance from the first sensor to the subsequent sensors denoted by dm, so this small m, so m equal to from 1 to big M, and d1 is 0 because it's the distance from the first sensor to itself. And then the beamformer output, you have apply a weight vector Wm, and you get the beamformer output. Then the sparsity-based design for sensor location optimization can be described by these 2 steps. First, consider the array geometry being a grid of potential active antenna locations. You don't know where to put the antenna yet. So in this distance, so dm is the maximum aperture of the array, and the values of dm are selected to give a uniform grade. It's not necessary to be a uniform grade, but because it's very dense, so we just consider it's a uniform grade with m being a very large number. So you have large number of potential antenna locations. In this case, the spacing between adjacent antennas is very small. And through selecting the minimum number of non-zero valued weight coefficients to generate a beam response close to this desired one, a sparse array design result is obtained. So in other words, so if a weight coefficient is zero valued, the corresponding sensor will be inactive and therefore can be removed, leading to a sparse or non-uniformly displaced sensor array. So here is a formulation, basically PR, this one is a vector holding the desired beam responses. Then WHA is the beamformer response. You limited these two, the error between the desired and designed, to a small value epsilon. And then you maximize the sparsity of this weight vector. And if the coefficient one entry in this weight vector is zero, that means the corresponding antenna is not needed to meet this constraint. So as a result, can be removed from the potential antenna locations. So at the very end, after optimization, you get the optimized antenna locations. As in many other L1 norm minimization problems, the reweighted L1 norm minimization could be used instead to have a closer approximation to the ideal L0 norm minimization problem. So this is reweighted L1 norm minimization. Replaces standard L1 norm minimization. Sometimes can give you a better result. Here's a design example. So you have the maximum aperture is 10 lambda, and we split this 10 lambda aperture into 181 potential sensor locations, and then you do the optimization. You will find out, okay, that's the magnitude of the weight coefficients. You see, many of them are zero already, and so only, okay, in this case, you have 12 left with non-zero valued coefficients here. And then if you compare this design with a standard uniform linear array with the same number with 12 sensors, you see the response, the beam response. Clearly, this sparse array is much better than the uniform linear array. So various constraints can be added to the standard formulation to deal with more complicated application scenarios. For example, you can deal with these model errors like robust design, or you can also consider the antenna size, because if you don't consider the size of antenna, the resultant sparse array, some of the sensors may be too close to each other. You can't fit into the sensor into the obtained locations. They're too close. So you can put some size constraint into the design. And you can also extend the design to the wideband case using group sparsity. Now the fourth topic is target source localization based on sensor arrays. This is another important problem. And you can use received signal strength or use time arrival information to find the location of a target or source. You can also use DOA information, so AOA, so angle arrival or DOA. So in this case, we call it bearing-only localization. There are normally two steps in this bearing-only localization. The first one is applying existing DOA estimation methods to find the AOAs at all distributed sensor arrays, while the second step is to find intersections of those estimated AOAs. However, so its performance, so the performance of this two-step method is dependent on the estimation accuracies obtained at all platforms. And even one bad estimation result can lead to a serious performance degradation. So there are also ambiguity and pairing issues associated with this two-step solution. Now, to tackle this, the shortcomings of this two-step approach, then one recent advance is this group sparsity-based solution, where this common spatial sparsity support corresponding to all distributed sensor arrays is enforced, leading to a better estimation performance, which also avoids the possible pairing and ambiguity problems associated with the two-step solution. And to show how this method works, we just consider this distributed narrowband sensor array network with M subarrays and K targets. So here's a scenario. So you have this target, you have these platforms. Each platform carries a subarray. And for each target located at this position, a unique incident angle theta mk relative to the M subarray can be obtained. Without loss of generality, a square area of interest is divided into a kx by ky grid, with kx and ky being the number of grid points along the x-axis and the y-axis, respectively. And this g xkx yky represents the location of the kx ky search grid, and the signal originating from the possible source located at this g xkx yky will arrive at the M subarray with the DOA angle theta m g kx ky. And since this xkx yky is common to all subarrays, and the source located at this location G will appear to come from the same location with respect to all subarrays. So we can apply the group sparsity concept to all subarrays source data. So here, this is the standard model, multiple snapshot model for each subarray. So you have big M of them. For each subarray, you have this formulation. And then again, you construct this overall complete model. You have this result. And then for all the subarrays, so big M of them, you put the source matrix into a much larger matrix SG, big SG. So this is a source matrix of the first subarray. This is the second subarray, and so on. So if there's no signal for a particular location, then the corresponding row vector for this S1G will be zero valued. And there will be the same corresponding row vector will also be zero valued for this S2G, and so on. So you put them into this big matrix, the whole row. If there's no source signal for a particular location, then the corresponding row of this big matrix SG will be zero valued. So based on this idea, you can minimize the L2-1 norm of this SG, and subject to limiting the overall reconstruction error for all subarrays to be a small value. And in this approach, so different subarrays are not required to be synchronized and can work on different frequencies. The statistical properties of the sources can be different for different subarrays, and sensor numbers, rotation angles, and the corresponding source signals of different subarrays do not need to be the same, as long as they come from the same set of target locations. So, and this idea can be extended to either the wideband or the underdetermined case, or both, without difficulty. So here is a simulation result. We have 5 targets, 6 subarrays, which with each being a 4 sensor minimum redundancy array, and 20 dB SNR and 500 snapshots. You can see the result. All of them have been identified correctly. Now the 5th topic is multiple input and multiple output arrays, so MIMO. And there are two totally different directions. So one is the MIMO radar. So MIMO radar exploits the orthogonality of the transmitted waveforms to increase the DOFs for improved resolution and capacity, which will play an important role in 4D auto radar imaging, in addition to traditional radar detection applications. And the other one is MIMO for wireless communications. So MIMO has already been in use for both Wi-Fi and 4G communication systems. Its new evolution, the so-called meso-MIMO or ultra-meso-MIMO, will play a crucial role in the next generation communication systems and beyond. First, MIMO radar. So in MIMO radar, multiple transmit antennas emit orthogonal waveforms, and multiple receive antennas then receive the echoes reflected by targets. Its antennas can be widely separated or co-located, with the later one more widely studied. For the co-located case, the transmitting side and the receiving side can be located either at the same site or far away from each other. Now consider a co-located narrowband MIMO radar system. So where the transmit and receive antennas are located at the same place, and the transmitted multiple orthogonal waveforms are then reflected back by big K present targets and received by the receiver array. And after match filter processing, the output signal vector xi at the receiver side at the ith snapshot can be represented by this equation. So in here, this AT is the string vector of the transmit array, and AR is the string vector of the receiver array. And then it's Kronecker product of these two. You generate a new virtual string vector, and BKI is the virtual source signal. And because of this Kronecker product operation, you have for this new model, you have a much larger virtual array now. For example, if both the transmit array and the receive array are 3 sensor URAs with spacing of D and 3D respectively, the newly generated virtual URA will consist of 9 sensors. Now, MIMO for wireless communications. On the other hand, so MIMO for wireless communications is a huge research area, and numerous techniques have been developed centered around this concept, such as space-time coding, MIMO beamforming, spatial multiplexing, and spatial modulation, and so on. So here we only give a brief introduction to MIMO beamforming, which is playing an increasingly important role in the implementation of MIMO communication systems. So as well known by the array signal processing community, traditionally, so beamforming is designed for line-of-sight transmission and reception. And physically, a beam will be formed in the process, pointing to different directions around the array system. On the contrary, in MIMO beamforming, due to a very strong multipath effect, the result of beamforming between the transmitter and receiver will not necessarily form a beam in space, but rather an overall enhanced signal transmission link between them. So decades of research in MIMO beamforming have pushed the boundaries of beamforming well beyond its traditional meaning, and nowadays, any process achieving enhancement of the desired signal while reducing the effect of interference can be considered as beamforming. However, with the introduction of MIMO and the millimeter wave communications in 5G and beyond, the line-of-sight case is becoming more and more important again in MIMO beamforming. And one interesting development in this context is a hybrid beamforming structure proposed for MIMO systems. So hybrid beamforming is a combination of analog and digital beamforming, and it's mainly for reducing the cost and the power consumption of a fully digital implementation for large array signals. And there are many hybrid beamforming structures, and one representative is the sub-aperture-based hybrid beamformer. And one interesting recent development is a new class of multi-beam multiplexing designs where the number of analog coefficients is the same as the number of antennas, and independent of the number of parallel independent user beams generated, while the number of subarrays is the same as the number of beams. So you can find more information about this design in references 58, 59, and 60. Now, the third part, so 6 new developments in SAM. In the era of artificial intelligence, multi-sensor-based systems and techniques are ubiquitous and will play an even greater role in the future. So as a result, there has been exponential increase in research activities in the SAM area in the past few years. And we'll talk about, basically introduce 6 new developments into the area. The first one is a GSP for sensor networks. So graph signal processing is a new mathematical tool for analysis of data resident on a largely irregular network of either physical or virtual sensor nodes, where a regular network can be considered as a special case. So examples for the physical sensor network include traffic networks, brain networks, neural networks, the energy consumption sensor networks. While for this virtual one, a good example is social networks. In connection with classic signal processing, basic concepts such as frequency and operations such as shift, delay, and filtering have been introduced. However, it seems that there's still no unified framework and still an open problem to find the best representations of graph signal. Application of GSP to traditional array signal processing problems is an emerging but somewhat open area, as traditional sensor arrays and networks normally have a regular structure, and the traditional tools have been extremely successful in tackling those associated problems. And one most recent example is a new GSP-based DO estimation algorithm for narrowband arrays, where the DO estimation problem is treated completely using the language of GSP. However, it's not clear yet whether GSP can bring any significant advantage to the traditional array signal processing problems or not. A second development is tensor-based array signal processing. So tensors are extension of matrices to higher dimensions and have been widely employed for multidimensional data analysis and processing with the aid of tensor decomposition tools and algorithms. And many sensor array signals and data can be transformed into a multidimensional form or viewed directly as a multidimensional structure. For example, so narrowband data received by a rectangular array or subarrays are three-dimensional. Data received by a wideband linear array can be transformed into the 3D space-time frequency domain. The data received by a vector sensor arrays is naturally higher dimensional. For MIMO communication systems, the data can be replaced into a tensor form by accounting for diversities in space, time, frequency, and polarization. As a result, so tensor processing can be applied to solve many array signal processing problems directly without much adaptation. However, although it's recognized that tensors can keep the inherent data structures and therefore have the potential to provide improved performance compared to classic array signal processing methods and algorithms, further research is needed to demonstrate the clear benefits of tensor processing and fully realize its potential. The third one is quaternion valued array signal processing. As a higher dimensional extension of complex numbers, a quaternion has one real part and three imaginary parts. And quaternion calculus has been applied to a range of signal processing problems related to 3D, 4D signals, such as color image processing, wind profile prediction, vector sensor array processing, and quaternion valued wireless communications. So in addition to solving classic problems such as DO estimation beamforming, one important development is the quaternion valued MIMO array, where pairs of antennas with orthogonal polarizations are employed at both the transmitter and the receiver sides, and the 4D modulation scheme is a combination of 2D modulations. So a 4D modulation scheme across the two polarization diversity channels using a quaternion valued representation is employed. So this is also related to a more general topic about dual transmission signals. So two signals with different polarizations carrying different information are employed for communication. So although the polarization states will change through the channel, and there may be interferences between these two states, we can employ a quaternion valued adaptive algorithm to recover the original 4D signal, which inherently also performs an interference suppression operation to separate the original 2D signals. And for the memory, reference signal-based or blind quaternion valued adaptive algorithms can be employed for both channel estimation and beamforming. And signal processing has experienced the revolutionary change from real valued processing to complex valued processing. And we may be at the doorstep of a quaternion valued new world. And increasing interests for quaternion valued sensor array signal processing are expected in the near future. The fourth one is 1-bit and non-coherent array signal processing. So given the extremely high data rate and the storage requirements for a fully digital large sensor array system, there has been significant work aimed at achieving a reasonable performance with 1-bit representation of the array signals. So 1 bit means only signs of the data samples are reserved, while the magnitude information is removed. So this problem can be simply considered as the normal case, but with extremely high quantization noise. And we can perform normal array signal processing irrespective of the number of bits per data sample. However, a more effective way is to try to achieve effective estimation of the statistics of the signals using the 1-bit data samples, and then based on the newly obtained statistics information to perform the corresponding tasks. On the contrary to 1-bit, so the signs of data samples are removed and only the magnitude information is kept, which leads to the so-called non-coherent or magnitude-only sensor array signal processing problem, with the advantage of being robust against array phase errors. And one representative example is non-coherent DO estimation and target localization, which can be cast into a phase retrieval problem. However, the difference is there's usually only one snapshot in phase retrieval, while in array signal processing, multiple snapshots available. So you can, again, employ the group sparsity concept here. There have been some algorithms developed for this purpose, like Toybar and modified GSPAR. The fifth one is machine learning and AI for sensor arrays. So machine learning and AI have been applied to almost all areas of research in the signal processing community, and some area is no exception. So like DO estimation. Unlike in traditional machine learning and AI applications where it's a challenge to acquire sufficient training data, in most of the array signal processing applications, the required training data can be obtained easily by simulation. So nonetheless, the application to array signal processing also faces some similar issues. As an example, so after training, the system will work very well for the targeted scenario, but it may struggle if there's a change to the system or the environment. While the traditional array signal processing methods and algorithms can cope with such changes well. Another challenge is how to apply machine learning and AI to distributed sensor arrays and networks effectively. So as a hot topic, so federated learning may prove to be a promising direction research for the SAM community. The sixth one is array signal processing for next generation communication systems. So antenna array design and signal processing is one of the fundamental techniques in 5G and beyond wireless communication systems, since the two underpinning 5G, 6G technologies like massive or ultra-massive MIMO and millimeter wave sub-terahertz or terahertz communications, they are all based on antenna arrays. It will continue to play a significant role in many other aspects in the future, such as Internet of Things, integrated sensing and communication, so both of which are hot topics for 6G wireless communications research, with extensive research activities attracted in the community. Moreover, so beamforming is essential to achieve effective communication over the terahertz or sub-terahertz frequency band, as it's necessary to employ a large number of antennas for such high frequencies. While the widely studied reconfigurable intelligent services, so RIS, can be considered as a semi-passive antenna array system. So to a great degree, array signal processing will be a main focus of research for next generation communication systems and for the integration of sensing and communications. Now, conclusion. So in this talk, 5 main technological advances in the SAM area have been presented, including beamforming, DO estimation, sensor location optimization, target source localization based on sensor arrays, and MIMO arrays. So 6 new developments, which may well indicate promising future research directions, were also introduced briefly, including GSP for sensor networks, tensor-based array signal processing, Quaternion-valued array signal processing, 1-bit and non-coherent array signal processing, machine learning and AI for sensor arrays, and array signal processing for next-generation communication systems. And this is just one sample of 25 years of research in sensor array and multi-channel signal processing, and represents a biased view based on our own research experience and expertise. and more samples are needed to have a better estimation of the 25 years of research in this SAM area. Here is a list of representative references related to this talk. Thank you.